This video is about truth tables. Consider the statement, the sun is up and it is raining. One part of the statement could be true or false, and the other part could be true or false too. This is a compound statement. A compound statement joins together two or more simple statements with logical connectors. The overall compound and statement can only be true if both of the simple statements are true. Now, in a truth table, we can let two of the statements be represented by letters P and Q. P will stand for the statement the sun is up, and Q will stand for the statement it is raining. Here's the truth table. The different individual statements that were made are the columns. All possible combinations of both the time and weather are considered on the left. Those are just a guide for you. For each column, we'll say whether the individual statements P and Q would be true or false, given those time and weather combinations on the left. So if we check out the first row here, it says the sun is up and it's raining. Pretend those are the current conditions right now. Now, what if somebody comes along and makes the statement, the sun is up, and those are the conditions? Would they be telling the truth, or would it be a lie? Well, since the sun actually is up, according to the conditions on the left, if someone says the sun is up at that time, they would actually be telling the truth. And it's also raining at this time in row 1. So if somebody said it's raining, they'd be telling the truth. Now let's take a look at row 2. In row 2, it's a clear day. So if somebody says the sun is up, they are telling the truth. But if they say it's raining, then that's a lie. What if it's a rainy night and somebody says the sun is up? Did they tell the truth? No, they did not. But if it's a rainy night and they say it's raining, did they tell the truth then? Yes, they did. Finally, on a clear night, that's the other possibility out of the 4 here. If they say the sun is up, that would be a lie. And if they said it was raining, that would be a lie too. Our goal here of the truth table is to get all possible combinations of true and false. There's actually 4 different possibilities here. And we now want to consider the overall compound statement. So I'm going to write that in this last column. There's several ways we can write it. We could write P and Q. That's one way to say it. We can also use this symbol, which in logic stands for and. It's like an A without that middle bar. And we can also write it in words. I'll put the sun is up and it is raining. Okay, so when did they tell the truth overall? If somebody was to say the sun is up and it is raining, in what row would that statement really be valid? So there's only one row, actually. And the idea is that when you say an and statement, everything you say has to be true. If any one of the things you said was false, then the and statement would be false too. So if I say the sun is up and it's raining, and both of those conditions are happening at that time, so we have 2 truths here, then my overall statement is correct. But let's say it was a clear day and I said, the sun is up and it's raining. Even though I told the truth about one of the things, I lied about the other. And for that reason, we would say that the overall and statement was not true. On a rainy night, similarly, if I say the sun is up and it is raining, because I lied about the first thing, even though I was right about the rain, the overall and statement is still false. And then what about on a clear night? If I say the sun is up and it is raining, did I tell the truth? Well, no, actually I would have lied about both of the things that I said. So in that case, it would be false. Now what we have here is the general form of an and truth table. This type of form will always be found no matter what the situation is. Now let's try another type of truth table. Let's try a truth table for or. So once again, we have P and Q, and we just want all combinations of true and false. So go ahead and make a truth table for or on your own paper, if you have some. And see if you can fill in over here on the right, when would the or statement be true? I'll give you a moment to try it before I fill in my answers. Okay, so the first thing we want is we just want TT, TF, FT, and FF. In these types of truth tables where we have two statements being analyzed, we're always going to want that set of 4 different combinations. Technically, they'd be called permutations, but that's okay. All right, now we want to decide when is the or statement true or false. So on a rainy day, if I say the sun is up or it is raining, would I be telling the truth? Sometimes that's the hardest one for people to answer, because it brings up an important issue in logic between what is called the inclusive or and the exclusive or. And I'll just give you a brief example here on the side to hopefully make the problem clear. If I was to say that I'm going to shop at Tops or Wegmans, 2 grocery stores in the New York area, would you assume that that means that I might go to both of them? Probably not, right? You think if I say I'm going to Tops or Wegmans, you think I'm going to one or the other. Now that English meaning of or that we often use is the exclusive or. It means you could go to one or the other, but not both. And that in logic is sometimes called XOR to make it clear that it's an exclusive OR. Okay. But what we want to use here is actually the inclusive OR. Now in the inclusive OR, if I say I'm going to Tops or Wegmans, then it is valid to go to one or the other, or both. This is the meaning of or that we'll use here. Okay. So let's try to answer the question one more time with that understanding. I'll start with the easier ones. Let's say it's a clear day. If I say the sun is up or it is raining, did I tell the truth? Well, yes. In that case, because I told the truth about the sun being up, it's okay that I lied about the rain because it's an or statement. You just have to get one of the things right. What if it was a rainy night and I said the sun is up or it is raining? Did I tell the truth then? Yeah, even though I would have lied about the sun because it's actually nighttime, since I was right about the rain, my overall statement is correct. And let me try this last one here. Say it's a clear night and I say the sun is up or it is raining. Did I tell the truth? I hope it's clear that in that case, I did not tell the truth. The reason why is nothing I said was right. I was wrong about the sun when I said it was up, but it's actually nighttime. And I was wrong about the rain because I said it was raining when it wasn't. And that brings us back to the top one, which may be the toughest one. Let's say it's a rainy day, and I say the sun is up or it is raining. Did I tell the truth? Well, assuming that this or stands for the inclusive or, I actually did. In this type of or statement, as long as one or the other or both of the things you say are true, then we'll actually count that overall or statement as true. Okay, so let's now try to take this to a little bit higher level of logic. And we'll look at what's called a for all statement, sometimes called a generalization. In a for all statement, you're going to make a blanket statement about every member of a group. And so let's try it here with these dots, 5 dots. They can either be open dots or closed dots. Now let's take a look at this first statement. It says, in the above picture, the first dot is open, and the second dot is open, and the third dot is open. It strings together 3 statements with ands. Now, in order to count this compound statement as true, everything that is said has to be true. So, is it true? The answer is yes, it is. As we can see, the first dot is open, the second dot is open, and the third dot is open. Everything that was said is true, so the overall compound statement's true. But now let's try this next one. In the above picture, the first dot is open, and the second dot is open, and the third is open, and the fourth is open, and the fifth is open. Is the overall statement true? The answer is no. Because even though they told the truth about the first dot, and they told the truth about the second dot, and the third dot, and even the fifth dot, the fact that that fourth dot was not open means that that fourth statement right here was wrong. And so what we can say then is that dot 4 is called in logic a counterexample. And so when it comes to this last statement of all the 5 dots are open, that's just another way of stringing together several ands in a row, saying that all the dots meet this criteria of being open, but we know that they don't because of dot 4. And so the generalization there is false because of the counterexample dot 4. A conditional statement says if some property P exists, then some property Q must necessarily follow. In other words, P being true is sufficient for Q to also be true. Let's take the statement, if Alex is happy, then Alex smiles. Complete a truth table for that conditional statement. And I'm just going to draw some pictures here to give us a guide of the different possibilities. First of all, I'll put the meaning of P. Alex is happy. Q stands for Alex smiles. And in words, P arrow Q would be written as if Alex is happy, then Alex smiles. All right, so let's go ahead and draw some pictures just to kind of remind ourselves of what the different possibilities are. So I'm going to put happiness on the left and then smiling on the right. So I'll represent happiness with a heart. And the smile can just be a typical smile face. So what type of situation do we have here? Alex is happy, and Alex smiles. Now let's try the case where Alex is happy, but doesn't smile. Then we would have TF. Okay, now let's consider Alex not being happy. So I'll just do like a broken heart here. And maybe he's putting on a smile face regardless. That would be false, true. And the fourth possibility is not happy and not smiling. All of these four things are certainly conditions that could happen in reality. But let's say that Alex makes the statement that if he's happy, then that will lead to smiling. And we want to see when would the statement be disproven. Okay. So if you come across Alex and you know that he's happy and smiling, would that be evidence in support of the conditional statement, or would it be evidence that refutes it? Well, so far, there's no problem with what was asserted. Alex said that happiness would lead to smiling. We see that he is happy and smiling, so we definitely don't have evidence against the statement. But what if we come across Alex and knowing that he's happy at this time and not smiling? Would that be evidence in support or evidence against? The answer is that would be evidence against. He said that happiness would lead to smiling, but we see here that happiness did not lead to smiling. So that disproves the conditional statement. These next two are kind of the toughest ones. So, what if we come across Alex and we know that he's not happy and smiling? Is it evidence in support of the statement, or evidence against, or neither, perhaps? A lot of times people want to put false for this, but the fact is we can't, and here's why. The statement tells us what happiness leads to. It says that happiness leads to smiling. it doesn't talk about what unhappiness leads to. And so we can't use this case as evidence against the statement because we didn't meet the initial condition of Alex being happy. And for that reason, by default, we're going to leave it true because we haven't disproven it yet. And hopefully it's clear that in the fourth row, if we see unhappiness and frowning, well, that doesn't really pertain to the conditional statement that was made. And so we're going to leave that true as well. So there's only actually one way to disprove a conditional statement. You have to start with the condition of meeting what was talked about in P, the happiness. He's got to be happy. And then we have to show how it didn't lead to the conclusion of Q of him smiling. Okay, so if we do find him happy and not smiling, that would be what's called a counterexample. Okay. Let's try a little practice with it, with conditional statements. Decide which of the following conditional statements are true and which are false. If you believe a statement is true, then go ahead and provide examples which support that claim. But if you believe the conditional statement is false, then you should provide a counterexample which shows the statement is false. I'll do the first one, and then I'll let you try the second one here. First one says, if a number is whole, then it is also real. Does it seem like it's true or false? You have to think back to the number sets that we had looked at. In the one case, we looked at whole numbers, starting with 0 and counting up from there. So here's just a few examples of them. And they go on forever, but they're only on the hatch marks. That's the wholes. Now we should also look at the reals now. If you recall, the reals were everywhere on the number line. Okay, so are there any whole numbers here that are not also found on the real number line? The answer is no. They're actually all going to be found on the real number line. This is actually a true conditional statement. Now, what's another way that we can see that this is a true conditional statement? Well, you could also draw a Venn diagram showing the reals and how that bubble actually contains the wholes. The idea being, if a number is whole, such as 0, then it is also real. Why? Because the whole bubble is inside the real bubble. So if you're in the whole bubble, you can't ever escape the real bubble. So examples which support our claim are 0, 1, 2, and so on. They are whole, so they meet that initial condition of the conditional, right? And they are also real. We couldn't find any wholes that weren't real. But now, let's try the opposite here. If a number is real, then it is also whole. Can you think of a counterexample which would disprove that generalization? So think about it for a moment. All right, you may have guessed that the generalization is false, but we have to show evidence for why it's false. So can you think of a number that is real but not whole? I can think of one, a number that resides out here in the outer ring. How about the number 1/2? So 1/2 is real, but not whole. So 1/2 is a counterexample. Let's try to put a few counterexamples and examples into a truth table. So the column P stands for the number is real, and Q stands for the number is whole. And we're trying to decide whether if a number is real, then it is also whole. Is that a valid conditional statement or not? We actually just showed that it's not. And let's just go ahead and examine a few different numbers and see whether they are examples in support of the conditional or are they counterexamples which disprove it. So I'll start with a simple one like 1. Okay, and then I'll try 0.5. And maybe I'll do the imaginary number I, which is the square root of -1. All right, so for this first example here, number 1, is it real? It is. Is it whole? Yes, it is. So what should we put here? Is 1 evidence in support of the statement, or is it evidence against? If a number is real, then it is whole. Well, even though the overall statement may not be true, this particular example does not disprove it. We'd have to leave it as true because it meets the conditions. But what about 0.5? It is real, but not whole. So what should we put? Is 0.5 evidence in support or evidence against? It is evidence against. Now let's try the imaginary number I. Is it real? No, it's imaginary. Is it a whole number? Certainly not. The number I was not understood in ancient times when whole numbers was used for the first time. So what do we put? Is I evidence in support or evidence against? Well, the answer is neither. We'll leave the statement true by default because I alone does not disprove it. So out of all the 3 cases I mentioned, which one actually does disprove the conditional? 0.5 is a counterexample. Which disproves P arrow Q.